I thank Robert for arranging it for this intensive 24-hour course in UNCC. I've become an expert, or I've been exposed to a lot of wonderful things, and I thank many of you for that. I'm a little curious about who's here. One of the fun things about this discipline is that it brings together many other disciplines, and my background is in computer science and database and file design and optimization techniques, but I like to say that I've become 20% an experimental psychologist trying to study performance, and maybe 2% these days of a sociologist. So I'm curious, how many from the computer science department? Looks like a good crowd, more than half. From the software and information systems, right? All right, the other 20% from other engineering disciplines, mathematics, Harold, I know that, and biology. Bioinformatics, all right. Architecture, I heard we've got a few. What else? What else?
Health services.
Health services, great. What else? In the back?
I used to be an English major.
An English major, I love it. Okay, so it's that diversity that I find enriching and great fun. And the topic that I'm going to talk about today, about visualization, actually broadly applies to a variety of these environments. So here I wave the flag of the University of Maryland, and you can reach me here at Ben Shneiderman, at Ben@CS, but I really think I should change this and add my Twitter handle, since lately I've been doing a lot more on Twitter. So that's who I am, and you can find me there at BenDC. I'm happy to represent the University of Maryland's Human-Computer Interaction Lab, which is owned jointly by Computer Science and the Information Studies Department, the iSchool at Maryland, but has many other departments that it works with, including the wonderfully titled Maryland Institute for Technology and the Humanities, MITH. Come to our website. There are 450 papers, 200 videos, 40 software tools, and lots of other things to take a look at and see what we do. Also proud about the book Designing the User Interface. The first edition helped define the field. The fifth edition, now I'm joined as co-author with Catherine Plaisant, who's been my collaborator for 25 years at Maryland, and that tells this story of what's changed. The red highlights show what's happened since the 2005 edition, where, you know, Wikipedia and YouTube were just getting started, but Facebook and Twitter and so on didn't exist. Can you believe it? There was a time when Facebook and Twitter didn't exist. In any case, those have become such dominant forces. They're the leading websites that are visited on the web now, and they didn't exist 5 years ago. So the pace of change is enormous. The book has grown by having a full chapter about search and a full chapter about visualization. And we've had the pleasure of putting our ideas to work on many important projects at the Library of Congress, helping put the 7 million items in American memory, the handwritten letters of George Washington, the notebooks of the poet Walt Whitman, 200 collections of photographs, movies, scripts, and so on. We've worked for the Library of Medicine on many projects, maybe most well known as the Visible Human Explorer. We worked for NASA, which is just 3 miles down the road from College Park. We've worked for the Bureau of Census, and then that expanded to 70 different agencies, where with Gary Martini, my dear buddy, now at UNC, we worked to help them build websites that would enable citizens to find what they need and then understand what they find. Okay? So we see this role of public service as a real important part of what we do, and design of interfaces and increasingly visualizations is what makes it work. Most recently, I contributed to organizing or designing the recovery.gov website that Obama promised would show where every dime was spent of the $787 billion. In fact, the bill itself that launched this, on page 171 it says, "Thou shalt build a visual, user-friendly interface to let the public know." So these ideas have gone from an esoteric thing that a few academics, you know, Robert, myself, and others have talked about, to something that's in the popular culture. It's something that's a phenomena, that it's expected, and that not only recovery.gov, but data.gov, 500,000 data sets out there from government agencies that allow you to explore what's happening inside the government. I think this is a profound, radical, and permanent change which will have important aspects for the government and for our life. The lab has many other projects. I love to talk about this one of my colleagues Ben Peterson and Alison Druin, putting up 4,500 of the world's best children's books, books in 56 different languages. The interface itself is in 15 languages, and kids can search for books with red covers or books with happy endings or books about crocodiles, and they can find them and they read the full text, full color graphics of these books. It's a wonderful project that really is changing intercultural communication, language learning across cultures as well. And it's very nice they received the Social Impact Award from the ACM for this work last year. Okay, today's focus is about InfoVis. And I joined Stu Card and Jock McInlay in writing the book called Readings in InfoVis. Stu gave us the wonderful title, Using Vision to Think, which reminds us that it's not just your eyes as input devices, but that there's a mental process for understanding and developing insights. In fact, that's my punchline that I like to say. The goal of information visualization is not pictures, it's insights. Okay? So what we're building here are new tools, new kinds of telescopes or microscopes that let us see the phenomena that are usually invisible. They let me see, for example, look how hard I had to work to find out which departments you're from, and if I want to know where you went to high school, which countries you came from, what languages you speak, what programming languages you can write in, it would have taken me a long time. But I want special kind of glasses that I can look around, see the network of social relationships, see what's the most common, 60% computer science, 20% SIS, and a few little outliers, especially the English in the back, I want to know about the exceptions as well as the common patterns. And that's what we're building these days, tools that let you see it. The Hubble telescope I talk about social observation, or the Large Social Collider. And I want to tell you how we got to that idea. So, I'm not the only one who's been promoting this, but you may have noticed in the last 5 years that the small companies got bought by the middle companies got bought by the big companies, and that almost every product has visualization tools built into them. And I'm proud of our role with Spotfire, which started from our academic project, a paper we published in the Chi conference of 1994 with Christopher Ahlberg. He formed the company in '97. I served on the board of directors for 5 years, and I learned a lot about how business works. It's pretty admirable and impressive as well. And the company grew to 200 people and was sold in 2007 to Tibco. So it had a happy story, and it was great to be part of it. This is a shot of Spotfire in a discovery mode by Nick Thompson, a researcher at GE Health in England. And it shows the discovery of the RBP1 gene's unusual activity. That red spot over there echoed over here and over here in this coordinated multiple window view. Sliders, double box dynamic query sliders let you filter and select to get in on what you want. And that's the strategy that worked for Nick Thompson. And we see many other uses, but it's a high-end tool used in large companies. Pfizer, Novartis, AstraZeneca. Pharmaceutical drug discovery is its main success story. All 25 of the leading pharma companies in the world use this, and they have as many as 3,000 licenses to have a systematic approach to everybody doing this. Here you see 27 windows, and it's still, it's just enough to make sense of these complex data sets. So that's been a great satisfaction, and it's no surprise that people want more and more screen space. Pixels are what matter. So going up from 10 megapixels to 100 megapixel displays and beyond are really the right idea. And how do you get the right information on the display with the right resolution? It's not the inches, it's the pixels that count for me. Okay, so that's what we're after. There's also uses for small devices. And while I'm not sure I want the air traffic controller or my radiologist to do all their work on an iPhone, there's still a lot of utility to getting valuable information in a timely manner in your hands. So the lessons we learned from this 10-year process are, one of them is summarized here. A line I wrote down rather playfully, and then in the paper I published, I had 10 copies of this line, each representing one project where we struggled for weeks or months to find the design, and the principle became overview first, zoom and filter, then details on demand. And the idea was, even if you have 1 million or 1 billion records, show them all on the screen at once in some aggregated way. Show them what the extent of the data. Show them where the clusters are. Show them what the relationships might be. Show them where the outliers are. And that is a remarkable phenomenon that you can get in a short time. This paper, as a keynote at a conference, has generated up to 1,500 citations in Google Scholar, a rather remarkable amount. And I think people liked it. Well, people liked it, they built on it, they modified it, they refined it, they extended it, they contradicted it, and parodied it. It's a lot of fun to see how people take an idea. But what I think they liked is it asserted the centrality of human activity. It's not like some magical algorithm finds the insight for you. You have to look at the overview. You have to decide what you zoom in on. You have to decide what you filter out, and then you click to get the details on demand. So I'm going to try to show you how we did this in a lot of applications, and I want to sort of lay out the territory of InfoVis, separated from SciVis, the more 50-year-old discipline of looking at 3D models of the real world or 2D geospatial data representations. And what we're after is this new world of information visualization. Multivariate data, high-dimensional data, Spotfire and competing products like Tableau and ClickTech and Palantir and so on deal with these kind of data. Essentially, tables with, let's say, 10 to 200 variables are a comfortable place for us to operate on. Temporal data we're going to take a look at, tree structured, and then network data. There's a lot of fun blogs and websites, including, we should look at Eager Eyes, should add that. Robert's the blogger of renown for this topic as well. There's quite a few on there. And to motivate it, I'm going to start with just a real simple example. This is known as Anscombe's quartet. Anscombe was a statistician, and he developed this simple set of 4 sets of data. And I'm just going to ask you, what's interesting about this data? What do you see? There's 4 groups of data, only 12 lines. Anybody see anything interesting in this set of data? It's two-dimensional, that's right. There's an X and Y. Okay, I'll buy that. In the back? See anything interesting in the data?
I see 4 showing up in the fourth and the bottom row 3 times.
You see 4 showing up 3 times. Good start. Actually, that's a more general thing, right? Celine?
The X's are all integers and the Y's are all not.
Well, that's true. Right. Okay. What else?
There are few rows which seem to have higher values, like the first one, the third last one, the third.
Yeah.
They tend to catch your eye as having.
Because they're bigger. They're visually bigger. But there's other bigger ones here.
Yeah, because they have more to.
Yeah. Well, Bill?
Has 80.
All right. Well, that's pretty strange, right? Except for this one.
That's probably an outlier.
And, yeah? What do you see?
In sets 1, 2, and 3, the X column is the same.
Very good. It took a while to spot that these 3 columns are exactly the same. Okay. Now, if I ask you, can you visualize what these patterns look like? They're two-dimensional. So you say, you might say, if you're the statistician, data mining type, you'll say, I'll apply my statistical methods and take a look at them. But unfortunately, if you run this, they all have exactly the same mean variance of x and y, same correlation, same linear regression. So unfortunately, statistics doesn't always do it for you. But I'm going to show you these graphs, 4 graphs, and in about 400 milliseconds, you're going to know what these things are. Ready? Bingo! You can see right away a kind of pretty good linear correlation that's positive, a quadratic equation, and then here's a very straight linear with 1. Is that an outlier or an anomaly? I think that's an anomaly. I think it's a mistake. I don't think it's an outlier. Outliers are sort of, you know, reasonable, a little bit off the track, but that one's so far off that's probably a data error, okay? And this funny one has a different pattern here, okay? Now, I could put 4 more graphs which had the same statistical properties. In fact, I could have 4,000 more or 4 million. There's an infinite number of graphs that have the same property. And they would have different patterns that you would recognize, identify, and say, I understand something. So the visualization gives you understanding, gives you insight, is my claim. And this nice example from Anscombe tells you the story. Now, I'm going to put this to work and show you how we built interactive tools that let you explore. And the first demo is the time searcher. This is the PhD work of Harry Hochheiser. And this simple data set has stock market data. We were working on financial data, which you guys work on, as well as genomic data. And some of these 223 stocks go up, or some go down, some jiggle around. And we could look at them one by one and see if we could find anything interesting over there. But I've told you our principle is overview first, and so we plot all of them over here. This small, simple data set, gets us started. 13 time points, 223 stocks. Anybody see anything interesting here?
Divergence around February?
Yeah, February has a high volatility in the pricing. We see that right over here. And you train your eye and your mind to find it. And I can pick up my time box to explore it and say, OK, let's look at the peak. And I hope you can see that there. But the peak shows us that everything that went up in February went back down in March. And there's one interesting other anomaly, which is adaptive broadband, details on demand. That popped up. And it rose in January ahead of everybody else. Now, did the investors know something that the others didn't? Were they smarter than the others? Was there something special about this company? Of course, we have to dig deeper to know. But it reveals right away the kind of anomalies, the kind of outliers, the kind of interesting things, and the structures we might want to look for. I could look at the bottom, which is not so well pronounced, but there are a few other interesting things about the bottom as well. But our stock market and our genomics people both had the same question. They said, show me what starts low and finishes high. And so we're able to select that pattern of starting low, finish high. Can you see that? Or you want the lights down? Let's take the lights down. Quick, 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 quick. Is that better? All right. So, we can do these things, or you could create a pattern like this one. I want the stocks that start low, that go up, and then they stay up. That's really what I want. Let's get a few more of those. We could do that or select a little more. There we go. We got a bunch there that satisfy that principle. And I can take that pattern and go hunting all around during the year and look for those kind of patterns at different price ranges. And then again, our genomics and our financial people had the same question. They said, I want to see the things that go opposite. And we said, OK, we could do that. And so we built the flip. And the flip just goes back and forth. Now, this was submitted to a data mining conference. And one of the reviewers wrote that, well, there's nothing new here. It's just SQL greater than this, less than this, greater than this, less than this, greater than this, less than, yeah. And it's true. It's about 35 lines of SQL code, if you wanted to write it that way, which would take you about 100 seconds to write, I think, if you could do it accurately. But the capacity to move it around 10 times a second was what Harry Hochheiser achieved in this interface. And so I would say this is 1,000 times better than SQL in terms of exploring, discovering, and making insights. Okay? Any questions about this?
Which stock should I buy?
What's that? Which stock should I buy? That's your problem. Harry designed this to cover 10,000 stocks for 200 time periods, which is quite a lot of data, and he succeeded in still preserving the 100 millisecond update, and the computer science tricks were to make the high dimensional data run fast enough without doing disk access and so on, and he achieved it not by the traditional computer science structures of KD trees, quad trees, and grid files. Those didn't work once you got past 5 dimensions. And so rapid linear sweeps through arrays turned out to be the significant strategy for making that work. Well, there's lots more we could explore here, but this rapid, incremental, and reversible exploration was what the time searcher was all about. So you could open the window and close the window, and you could place things around. But I wasn't satisfied here, because you might say, oh, very nice, but you have to do all this hunting around here. Couldn't we automate the process of hunting and find the right place to put this pattern? And indeed, that's the kind of directions that we began to move in as we built more elaborate tools. Time Searcher 2. These are all free to download from the Time Searcher website. Chevron Texaco said, this was very nice, but we really need 10,000 time points, because they take the temperature and pressure at the top, middle, and bottom of every well, oil well, every 10 seconds for a year, and they've never seen their data. So we built this to do, and we achieved 10,000 or more, even though, remember, the screen's only 1,000 pixels wide, but we were able to do hundreds of thousands of time points, and we were able to make richer patterns. So you could select a pattern. This is weather data of sunlight, and so here's 2 cloudy days with 7 sunny days in between. And we just got sunny outside, so maybe we're the beginning of 7 sunny days. But you could look for similar patterns, and it would find them in the overview, and these red triangles indicate a match that's similar to it. And so these kind of accelerators really became very powerful. This little orange window is a 2-month period, and that's what's expanded in the detail view over here. Okay? And we built Time Searcher 3, which has some predictive forecasting, so you can take a look at those. These were temporal numeric sequences, a very important and well-studied class of data, but we began to become interested in other temporal patterns like patient histories, which had what we would call categorical data. And here you see the events of a patient visiting a doctor, and they have various events, flu, pneumonia. The patient is currently pregnant and is predicted to be pregnant for the next 2 months. They've been diagnosed with diabetes. They're getting insulin, increased dosage of insulin, and Lasix to counteract the side effects. If you click on the sonogram, you get the sonogram, and there's the fetus if you hadn't noticed. If you click on the blood test or X-ray, you'll get an X-ray or EKG. Okay? This here, the design goal was an overview that was 100 years of a patient history with 10,000 medical events. And we were, developing this to show a single patient's history. And these strategies have been embedded in about half of the current electronic medical record systems in various forms. But our aspiration was to go even further and say, I'm not interested in one patient. Well, I am interested in one patient, but I'm interested in 1 million patients. And if I have 1 million patients, can I find patterns of treatment and cures in that? And in fact, that was our most recent project. Last 4 years, David Wang finished his PhD a year ago now, and is working at Harvard Medical School and Partners Healthcare. And I'm going to give you his 4-minute video that describes this system.
In this demo, I'm going to show how to use LiveLines 2 to find patients who experienced decreased renal function, possibly as a result of the administration of their radiology contrast procedures. This is indicated by their creatinine high events within 2 weeks after radiologic contrast. Here I have loaded a data set of 3,598 patient records. Each record is represented by a horizontal strip containing the patient ID and the events in the patient's history.
Maybe I should just stop and say, I hope you can see the numbers. This is a 20-year history from this hospital from 1990 to 2010. So certain patients come in. This patient came in 1997. They come in at different times. And what the text was referring to, it's radiology contrast is injection you get to reveal the patterns of circulation in your kidneys, renal. And so what the unfortunate side effect is that 7% of the population have an adverse response to the injection of contrast, and you test for that by measuring the levels of creatinine. So you test before they take the radiology contrast. You want a low level, and then you're going to give them the radiology contrast, and then in the next few days you'll test to see if they have high creatinine. That's the danger sign that we have to hunt for, okay?
Each event is represented by a colored triangle on the timeline. From the legend, I see that creatinine high, normal, and low are in red, blue, green, respectively. Scrolling down, I see that radiology contrast events are in yellow. To examine this data better, I align the patient records by their first radiology contrast events and rank by the number of creatinine high events to bring the most severe patients up the top. I immediately realized two things. One, some patients have chronic renal deficiency and they should be removed because their condition is not related to their radiology contrast. Two, some patients have more than one radiology contrast events, and this needs to be taken into consideration. To remove the chronic patients who have at least 4 creatinine high events prior to a radiology contrast, I choose to filter by the number of occurrences on creatinine high. I set a number to be at least 4, and the filter scope to be before the alignment. The blue highlight indicates that these records are selected. For our purposes, we want to remove them. I click on Remove Selected, and also save the remaining records as a new group. It's called non-chronic. Next, instead of aligning by every patient's first radiology contrast, I align by all radiology contrasts in all patients. Lifelines 2 asks me whether I will proceed, as some patients will be duplicated. I click on Proceed. Then I bring up the distribution of creatinine high events across these records and zoom into the granularity of days. As I drag from day 1 to day 14, I'm selecting all patients who have at least one creatinine high event within 2 weeks after any of their radiology contrast events. This time, I will click on Keep Selected and save these records as, let's call it candidates. Looking at this group, we see that this is more of an overestimate. Many of the patients do not exhibit patterns of contrast-related renal deficiency. It would be better if we restrict only patients who have a baseline of normal creatinine prior to their radiology contrasts, without creatinine high events in between. To do this, I will use a sequence filter, specifying only for patients who have at least one creatinine normal reading, followed by no creatinine highs, followed by radiology contrast, and finally followed by at least one red compromise. Likewise, I'll click on Keep Selected and save this as a final group. Finally, this gives us 157 records.
All right, I think I'll stop it here. That sequence search, where there were 4 events in a row, is really difficult to write in SQL. We went to 6 database professionals who worked on this medical data set. Not one of them could write that query correctly, especially because it included the absence of a certain event. Those are really tough to write. Furthermore, even if they wrote it, it would take weeks to run this query because 4 self-joins would produce a huge intermediate data set that just taxed the servers, the SQL servers that this was running on. So we've had 11 experiments, or let's say case studies, with our physician friends where they've put this to work to find patterns of treatment and outcome in their hospitals that they were unable to find in any other way. If you're working on categorical data, especially medical, we'd love to talk with you. We've developed not only this tool, but its successor tool now gives you better overviews of the whole structure to show the common patterns, so that if you're interested in what happens to cancer patients who get chemotherapy, radiation, or surgery, you can see what the outcomes might be and then make a decision, a better decision for your patients. Any questions about this before? It's a little difficult. You can see the video on the Lifelines 2 homepage. Did I see a hand in the back? All right, I think I'm going to move on. And just say a few words about tree maps, a favorite topic of mine. Thanks to Robert for mentioning it. We had developed this idea in 1990, 91, 92. It got a lot of popularity when in 1999 Martin Wattenberg made the Smart Money Market Map, which shows you 600 stocks. And this is free on the web still. The area indicates the market capitalization of the company. They're organized in 11 industry groups. The green stocks are rising, the red stocks are falling, and you can get something of an overview. Now, sometimes it really produces interesting patterns, like this one. Anybody see anything interesting here? This is a bad day on the market. You see anything interesting? Yeah, one green, it's not just a little green, it's bright green. And when I clicked on that, the details on demand comes up, and I found out that that was the A&P Trading Company, which owns grocery stores. And that day, they bought the Pathmark chain of grocery stores. They were up 6% when everybody else was down. And I love to show this example because it's one of those principles about InfoVis and visual analytics that says it gives you answers to questions you didn't even know you had. Okay? Once your eye is trained and understands the structure of these, and there may be some learning and visual literacy, but the idea of getting answers to questions that you didn't even ask is pretty powerful. So here's another pattern. Can you see this here? Technology is up, energy's up, but financial and healthcare are down. I mean, that's sort of, you begin to get more subtle patterns. And then this one was pretty interesting, and this happens often, is these were down when the rest was up. These are the gold stocks, and they often go the opposite of the way the market. When the market's happy, then the gold stocks are down, and vice versa. This is a little better. Oh, I know. This one I include. I just grabbed last week or 2 weeks ago, a few weeks ago. Yeah, 2 weeks ago, 10 days ago. But this was a pretty interesting one. What happened on this day when most of the market was up, but Sprint was down 16%? That's a huge drop in one day. That's it. Bravo. You know the story. If you clicked on N, it's for news, and that would have told you the story that that day AT&T bought T-Mobile, which was seen as good for them, but bad for the competition of Sprint, and Sprint dropped 16%. So these kind of events stand out, and they're sort of memorable when they're seen visually, and you can spot them and learn about them. Many other people have taken tree maps in other wonderful ways. A 26-year-old programmer, Marcos Westkamp, made this news aggregator that used tree maps, free, still on the web, Newsmap. You can take a look at that. I work with a company and they've licensed our software called the Hive Group. Their tools have become famous and widely used. I'm going to breeze past them. Spotfire now includes tree maps with all its powerful filtering facilities behind it. New York Times in 2007 began using tree maps with this very ambitious one that shows 6 variables in the automobile industry, cars and trucks, foreign and domestic, increasing and decreasing sales, etc., etc. And it was a great example, and they continue to use tree maps on a regular basis. They even boldly went to the new kind of tree map by Michael Baltzer, Voronoi tree maps, to show the inflation patterns. I'm not sure that visually it's easy to compare the sizes here, but it sure looks nice and is catchy and attractive to the eye. For scalability, we did do a 1,000,000-node tree map, and I could talk for about an hour about the discoveries in here, but I'll just point out one of the insights was about 7% of the data was ungarbage collected storage that nobody knew about, and that, you know, hundreds and hundreds of gigabytes was being wasted because it just was sitting there and clogging up the servers. Okay. What I really wanted to get to and leave time for questions was about network visualization, which I've seen as the toughest problem and the one that I've saved for myself for the last, and the current challenge that we're working on. If you want to learn about it, there's ironically a page, a wonderful page called Visual Complexity by Manuel Lima, 751 projects of networks, but mostly they're bowls of spaghetti. They're pretty as posters. They're big splatters of color and so on. And I saw in the dean's office the famous peacock map of the internet. It looks pretty, but it's not clear what you can learn from that. And so we began to develop network visualizations that were more meaningful. Here, the PhD work of Adam Perrer. This was a terrorist analysis based on the terror data sets, the global terror database that's kept by the University of Maryland's START program. But I'm going to show you a little 1-minute video that shows the voting patterns in the US Senate during 2007. Now, I hope you know there are 100 senators, and the red Republicans and the blue Democrats are highlighted here. The 2 independents of Lieberman and Sanders are shown over there. And we had the voting patterns. We were brought the voting patterns by a journalist named Chris Wilson, who was looking at how similar were the patterns of voting of different people. During 2007, there were 330 votes in the Senate, and 2 senators, they're ranked by their similarity. Cardin and Mikulski, ironically both from Maryland, those are the 2 senators from Maryland, voted 303 times together, exactly the same way, all right, 90% of the time. And then it goes down all the way to about 60 votes of similarity. So that gives us a link between every pair of senators. So if I have 100 senators and a link between every pair, 100 choose 2 means how many? About 5,000 links. Quite a mess to look at. But here we're going to sort it out for you. So what we do, whoops, let me press play. We start by filtering out the low ones, the 110, 120, 130, 140, and we use the force-directed algorithm to relay out the network. Now, John McCain was out campaigning for president, so he didn't vote enough times to be connected to anybody. 150, 160, 170, 180, 190 to get the high similarities. Brownback was also campaigning for president, and we get this unbelievable, remarkable, too good to be true result that came really from the algorithm. We didn't set this up, and there it is. And the stories you can see are that the Democrats vote as a pretty tight block, and the independents are with them. Republicans also have a pretty tight block. There isn't a lot of overlap, but there are 3 senators who are likely to go closer to the Democrats. Olympia Snowe from Maine, Arlen Specter, Pennsylvania, and Susan Collins from Maine. And what do you know? 2 years later, when the stimulus bill was voted on in the Senate, those were the 3 Republicans who crossed over to vote in favor of the stimulus bill. So it's pretty remarkable in terms of its predictive power. Now, you can see a lot of other factors here also. Far away from the Republicans, Dodd, Biden, our vice president, Kerry, Mikulski, and Obama. So they were really far away from the Republican, and actually they're on the periphery of the Democrats. The tight ball in the center of the Democrats are a lot of the Midwestern Democrats that form a tight caucus and vote together quite consistently. So this was rather remarkably revealing of the patterns of voting. And just to make it extra sweet, the red Republicans went to the right and the blue Democrats went to the left. It was just, you know, too good to be true. If I let this run another few seconds and we filter out the higher similarities, 210, 220, 230, we'll see that the Republican links begin to fall apart, and the Republican Party cohesion has collapsed at the high end, and only Isaacson and Chambliss vote similarly, whereas the Democrats, those Midwestern Democrats, have kept their party cohesion and remain a unified bloc. Okay? Yeah?
Now, Ben, this seems to be contrary to the, at least to my conventional wisdom, because I thought Republicans are a lot more closely associated with together than the Democrats.
And that has happened in later years, right, but not in 2007. Okay? So there are other people who then followed this up in their whole websites that show these patterns for successive years, and people have begun to look at this because this gave them a new tool for understanding what's going on. But this dramatic result, which is counterintuitive, totally surprising to me. I thought there would have been more overlap, was what I would have expected. And I didn't realize that the party cohesion was so different from one to the other. All right. There's a lot more. You can look at it on the website. And I want to turn to my final topic, which is the application of network analysis to social media. This, I think, is our great adventure for the next, not just decade, but probably next century, to try to understand the patterns in the sand. The people who walked on the beach, was it a man, a woman? Did they walk together? Did they have a dog? Did they come back an hour later? What's going on here? And we have that kind of patterns in the sand with the 1 billion tweets per week that are issued on Twitter, and the many comments on Facebook and all the other social media. So we've built a tool called NodeXL, free to download, supported by Microsoft Research. This is now more than 4 years in the making. And it's embedded in Excel. So you simply type in your network and invited Bob to a party. Bob invited Carol. Carol invited Dave, and so on. I type these in, and you draw the graph. If you can make a pie chart, you can make a graph. You can then set the visual attributes, make the girls pink and make the boys blue, put the names on the screen, and do more and more. And if you do the Senate data set, we give you that as well. This is what it looks like inside NodeXL. So you can explore with that, and here's all the voting patterns and all the controls for color and so on. Its interesting power is that the import box lets you import your email or Flickr, Twitter, YouTube, Facebook, and other data sets. So that alone would make NodeXL a valuable tool because it gives you non-programmable. You don't have to do the APIs. You can just go and grab the data sets. And here's the dialog box so you can get the different relationships. And when we began to do this, the first early occasion, my collaborator Mark Smith did this one. In September 2009, there was an important conference at NYU in New York called Workshop on Information in Networks. And about 80 people had assembled, and there was a feeling that there was a bunch of sociologists over here and a bunch of computer scientists here, and they weren't quite talking to each other. Mark Smith downloaded all the people who tweeted hashtag Win09. And sure enough, when you plot their relationships, you see this remarkable pattern of the sociologists, who are more numerous and active on Twitter. Barry Wellman, a famous sociologist over there, and grad student, a very active grad student here. And he's a blogger, Drew Conway. And then the computer scientists were over here. They were fewer in number. And one grad student at MIT who was the bridge between them. Okay? And this kind of split between communities is something we see quite often. On the other hand, some communities are tightly woven together. This was the World Wide Web Conference of 2010, and it's a very tight community. They do follow each other. It's a much bigger community, and they're all quite woven together. Vint Cerf is among them, and only a small number of them are disconnected from that main graph. These are sort of isolated people who don't follow each other, but they did tweet the string worldwide www 2010. We've just done the 2011 one. I should have put it in my slides. It was last week in India. And if you go to Mark Smith's web page and Flickr page, you'll see the pattern for 2011 in a much nicer visualization format. Some topics are more fragmented, like the topic HCI has actually several meanings. Human Capital Index, all of these red people, our clustering algorithm did the coloring of all these red. They're separated from, I hope you can see, the people who tweet HCI. They're over here in several clusters. This cluster is a bunch of Japanese researchers, and the big one is RKMT, who's Jun Rekimoto, the head of the Sony computer science lab in Tokyo. He has 160,000 followers on Twitter, so he stands out. And then a lot of people in small groups over here. When we did the oil spill last summer, we found another standard pattern of controversy. These are the people who are talking about it as an environmental disaster, as an economic problem. USA Today, NPR, news organizations, and so on, who were concerned. These people were the climate skeptics. They knew each other quite well and were well connected, but there were very few links across, just a few that bridged that group. Okay? And then a lot of people, as happens with terms that are very generic, like oil spill, are just not connected with the main community. So here, more than 50% are disconnected. There is not a well-formed discussion around oil spill. Okay? Another way of looking at it was the Chi conference of 2010, which we plotted here. Instead of the network relationship, we laid them out by the number of followers on the x-axis logarithmically and the number of tweets on the y-axis. And you see a distinct outlier over here, Zephoria. Anybody know Zephoria? It's a woman named Dana Boyd. She's a researcher for Microsoft Research. She's a remarkable, very interesting woman. And she has more followers than anybody else in that community. Okay? She wasn't even at the conference, and she was tweeting about it, and people were following her. But she's not the most frequent tweeter. There are some people who tweet a lot. Okay? But she doesn't tweet that much compared to them, but she's still the most followed by a long way. And she writes very interesting comments and has a lot to say. Now, the people below the diagonal are the successful people. My buddy Mark Smith's over here, and there I am below the diagonal. A little quieter. I've gotten more active. If you follow me, you'll see that I'm trying to use this more actively. The people above the diagonal are the losers. They tweet a lot, but nobody listens. In fact, over here is a voice bot where it tweets all the time, but nobody follows them at all. Okay, in this community, in any case. We applied our clustering methods to, this is Flickr. We downloaded all the Flickr photos that use the tag mouse, and we found remarkable clustering that shows up as the yellow cluster of computer mouse. This is the red cluster of Animal Mouse, and this is Mickey Mouse. And these are the photos over here. And they form really distinct. The clustering algorithm was highly successful in separating them out. If I show you my own Flickr stream with names, you'll see that my family pictures are over here. My 2 daughters are over here. There are 28 photos in which I appear with my daughter Anna, 25 with Sarah, 39 of the 2 of them together, and Sarah's married to Mark, and there are 93 pictures of them that I've taken. So that's sort of, and my sister's over here and her family and so on. Our lab group is the green cluster over here with a few friends who hang out with us pretty often. But you can see Catherine Plaisant and Jenny Priest and Ben Peterson, Alison Druin, and then a few others. Then there's a bunch of here IBM people, and then other people from the Chi community. And so the clustering algorithm, while not perfect in this case, the other one was just remarkable, but you'll see some famous key people like Jim Foley and Don Norman and Stu Card and so on that you may recognize in this clustering. So the book is here. This copy is for Robert, and I'm very pleased with just out a few months ago. And it's grown in a lot of interest and gotten some wonderful reviews. So I hope you'll take a look at it. The tool is free to download. I'm teaching with it in my class. And you know, the first 3 are sort of the arguments about social media and how to do network analysis. The middle 4 chapters are step-by-step, walk you through the tool. And then we apply it to email, threaded networks, Twitter, Facebook, World Wide Web, Flickr, YouTube, and Wiki networks. And the capacity to be able to see these things, as I say, the Hubble telescope for social observation is pretty remarkable. And of course, a little dangerous. Is it an invasion of privacy? Is it problematic? But that's where we're going. We think it's quite exciting, and the capacity to understand these patterns of social discussion are what are so transformative. For the first time in history, everybody can have a voice, whether it's political discussions or currently pointed out in the Middle East and the uprisings in Egypt and Tunisia and Libya. Often Twitter is seen as an important force that helps bring that about. And so it's important to understand it. It's important to understand its dangers of the misuse of rumors, of malicious use, of scamming and spamming. But that's what the new world's all about. It's happening very fast. The growth of Twitter to 1 billion tweets a week and 300 million users is, I find, amazing. But the best is yet to come. So I'm saying it's the first time in history that everyone can have a voice. But it's the first time in history that we can really see what the community is doing. And we've been studying the networks that grow up around political topics, and we're getting a lot of interesting results that we're going to publish soon with the Pew Internet and American Society. This is the group that built NodeXL and continues to work on it. Cambridge, Microsoft Cambridge, England, Mark Smith, myself, and the group at Maryland, Stanford, Cornell, and others participate. And we've started the Social Media Research Foundation, a nonprofit which will own NodeXL. Microsoft passes it over. We hope to be as successful as Mozilla Foundation or Linux and Apache. Actually, I mean, social media is network analysis is still a smaller topic, but our goal is open tools, open data, and open scholarship. That's what we're after. We hope to promote greater interest in this topic. And I just close by reminding you that the powerful technology that you're studying, that we all influence, should be put to good work. And I want to be proud to be part of a discipline, professional community that takes this as part of its requirements documents: eradicating extreme poverty and hunger, achieving universal primary education, reducing child mortality, improving maternal health, and so on. These are the UN Millennium Development Goals that were promulgated in 2000. And sadly, after more than 10 years, the progress is slow. More good can be done, and I invite you to get to work on it. It's important, and I hope we will contribute to making a better world. And I close by inviting you to our annual symposium. Come visit us at Maryland, May 25, 26, or come see us online. Thank you for your time and attention. Glad to have questions. All right, I went through rather quickly, so if there are questions or challenges, yes?
I noticed in your network visualizations, it seems like you select a certain temporal aggregate. But I feel like, maybe in the politicians' data set, there are times, certain time spans at which there are hidden stories within time spans. Have you explored the...
We haven't done that, but there are a growing number of political analysis tools that let you look at that. So the Congress may, on a week-by-week basis, change its patterns of voting. Is that what you're suggesting?
Well, within the network, maybe there is a, if you select the right time span in the network, you'll see a new, group of politicians coming together to vote against a specific bill or something like that.
Yes, those kind of things are well studied in general in political science, so they will detect those. We hope these tools may help them see more subtle patterns, like ones we found, like the Midwestern caucus, that was not so widely known, but they do vote in a similar way. I also wanted to plug this. We've been working to develop interest on this topic, and we had an NSF grant to run 2 workshops, one on the East Coast and West Coast, on what we call technology-mediated social participation. In the November issue of IEEE were 7 articles that came from that. They're very, I must say, well done. I'm very pleased by the outcome of that, by the 60 people who participated in that process. And this copy goes to your dean. And there's one more for Robert, but I hope you'll take a look online. I do think this topic of how we can apply technology-mediated social participation to disaster response, health and wellness, community safety, environmental sustainability, biodiversity, these are all, I think, critical problems. We have remarkable potential with these tools to influence billions of people. That's the transformation from actually the 4th edition of my book to the 5th. While social media was an idea that's been around for a while, the fact that 5 billion people have cell phones in their hands and can participate changes a lot of things. And the potential to put that to work in good ways is what the opportunity your generation has. Use it well. Anything else? Yeah?
Yeah, I got a question about your manual. So essentially before all the visualization on the desktop where the data aggregation can be popped into manual, which is so sufficient. But right now, a lot of visualization are doing this remote server and client-based stuff. So constructing an overview become a problem because you cannot load the data all into the client server. Right. So I want to get your take on that.
So what we really want is a seamless kind of environment that works in the cloud, that works, on the web, on desktop, laptop, mobile devices, okay? And each of those present different challenges. The cloud is not always the best way to do things either. But in order to visualize 1 billion records on a cell phone, I need to aggregate, filter, and select and show some cogent subset or aspect of that, or some overview of relationships. But that's what we're really good at doing, and that's what the tools are good. So instead of showing 5 billion people, I can just show, of the phone calls that are made, how many are between men to men, or women to women, or between men and women, and which direction. So I could get a small little graph that aggregated the results in that way. And there are 100 different ways to aggregate those data. I could do it by country. Which countries have high degree of telephone communication, cell phone interchanges? Which pairs of countries have low degree? And that's our challenge.